Could I have your attention, please? So current is flowing. This side here is the red thing, so it flows out of the red terminal. It's flowing along this wire. They're both red. I should have picked a red and a black wire, right? But it's flowing into this thing, and I believe if you look at it, that means it's flowing this way. The current is flowing there, and it's flowing that way. Yeah? So shouldn't that be that this thing is going to become, if the current is flowing around and around and around and around, okay, shouldn't it be that that side is the North Pole of this thing, if I turn the current on? So let's turn the current on, okay? And let's turn it down, turn it there. And I'm going to turn it up to about 4 amps because it can sustain about 4 amps. It'll just get kind of nicely warm like that, okay? Now let me introduce you to this thing. You've seen it before, but there it is, and you're going to get to play with these. These things cost $16.95 because that's a rare earth magnet, and it's mounted and almost perfectly balanced on these like little sort of diamond gimbals. So please be careful. Don't like stick them to things. Don't be like fencing with them or something like that. Be very careful with these because that's a chunk of money for us to replace. Now, these magnet probes, the blue side is south pole, the red side is north. Red is north. Okay, so that's one of the ways, by the way, to identify a North Pole. Just look for the thing painted red. Okay, now, if this side toward you, if the current really is flowing that way, and that's a North Pole, which end of this is going to like that end? The south should like that end. So let's see. What side's facing you? North. Yeah, the north is facing you, which means the south likes that thing. And then you can stick this inside. That's the whole idea of this, right? And inside there, it's all happy. That North Pole, anywhere inside there, and you can see this because you're going to do this yourself. Okay, it's just sitting there and it's like, I'm happy, I'm pointed this way. And in fact, this thing is actually oscillating back and forth. It's like it's on a spring mount. It's like going like this, right? Because I shook it a little bit, right? But anywhere inside there, it's just like a dog pointing to a downed bird, you know, it's like a little pointer in there. It's exactly, and it's the magnetic field lines are axial. Inside there, they're oriented with the axis of this thing. And the reason for that is that if we just look at one of these wires, think about this wire, the current, okay, is flowing this way on this wire, yes? Which means on this side of the wire, it's this way, yeah? Do you see that as it goes around, do you see that all those wires as they go around on this side of the wire, that the magnetic field is this way? And so if you have those wires stacked up, stacked up, stacked up, stacked up, you're always on this side of the wire, and so the magnetic field is always, you're always getting that side of the wire, right? It's always the same side of the wire that's pointed out. Does that make sense? Okay, so this is called a solenoid, and if you wanted to have a perfectly uniform magnetic field, you would have a solenoid that's very long compared to its width. Okay, so that could be your magnet lab, is you could measure the field strength inside here, although it's going to be kind of hard to get the Hall effect probe the way they're configured down inside there. I think the new ones have like you can bend the tip or something like that. Okay, but you could actually do a cross section across this front here. Right, so your magnet lab could be, how does the actual magnetic field strength change with the geometry of this, right? Couldn't you also put the magnet probe here and manipulate this current? Couldn't you? Indeed you could, okay? And that, by the way, this would make a straight line graph. I'm not supposed to tell you this, but the magnetic field is directly proportional to the current flowing in this solenoid. That's not a formula we learned, but it is. Wouldn't that make a straight line graph? Wouldn't that graph have generous error bars on it? Couldn't you do the max-min slope on that? Yeah? Just an idea, right? So put the Hall effect probe here, keep it stationary, don't move it at all, don't move the coil, simply manipulate the current going through this. Take 10 data points, you're done. Yeah? Okay. Okay, so that's a solenoid, and I've shown you that, and yeah. Okay. Oh, by the way, which way is it on the outside? If it's toward you on the inside, on the outside it's the other way, right? So you can take it and go, I want you to take it and go around this way and show, it'll trace those lines out. Okay? Now, let's go to the next one. Okay, with a straight wire, and of course the problem with a straight wire is how do you get back to the other side of the straight wire? Okay, so for a straight wire, we're going to pretend that one side of this for the magnet probe lab, okay, is the straight wire. Let's undo this one. I like how it sparks, that's kind of nice, huh? Okay, and then positive side goes here and negative side goes there. Okay, And we think, how much current's flowing? Oh, a little less than 4 amps. So that means there's more wire in this thing. Okay. So we think that the current should go, we look around one side of this, right? Thumb in the direction of the current. You'll get to test this out, right? That means the magnetic field should go around the wire this way, anti-clockwise as seen from above, does it? So your magnet probe, when you're using it, remember it's just like a little arrow, and the red end is the tip of the arrow, the blue end is the tail of the arrow. And I can see this, you can't see it, but it's really cool. It's just sitting there going around and tracing a tangent as we go around. Tex can see it. There you go. So I want you guys to see that. That's what I want you to see. So with a straight wire, that's what goes on. And then a flat circular solenoid, or flat coils, well, this one's a square, so just deal with it, right? Okay. This side should be, inside here, it should all be, well, again, the current's flowing this way. Inside here, there should be flux that way, which means you should see which end, the red end or the blue end. You should see the red end like that, because that's the direction the flux lines are going. As you go out here, it should start to bend, just like it shows in that diagram there, right? And it's kind of cool, it's doing that, right? Okay, so sit there and map it. It does this, right? It's like, ooh, out here it's like, oh, I don't really care. Okay, you know, here we go. Okay, so that's and this is the heart of the Magnet Probe Lab, is to do that. Okay, another one you can do. This is a 1/r. This, if you measure the magnetic field strength and go away from this thing, probably go this way, right? If you just change the distance here, it's actually 1/r for that one. Okay, so you can. That'd be another thing you could do, right, is just do distance with this. Or you could do the cross section of this, right? That'd be kind of fun, right? Don't move this. Okay, so that's yet another thing you could do for the Magnet Probe Lab. Okay, and then the final thing is I've got the demonstration that probably will get me in trouble. So, not as much trouble as killing a flower baby, though. Okay, no, not this year. No. Okay, so, no, the story with the flower babies, I made a joke, and I thought this was funny. The teacher should actually get tags. Did I explain this whole thing? And that really, if we hunted the flower baby, it would make flower babies as a whole stronger, because the ones that we would be harvested, as it were, taken, would be the ones that straggle away from the herd and are probably weak, have weak genetic material, right? And so it's sort of like culling the flower. And besides, flower babies are made of food, right? So you could eat what you killed, right? You know what I mean? I mean, I think that's the main lesson behind flower babies, is that babies are made of food. You know?
If you leave your baby alone, somebody's going to eat it.
You know? Somebody like a predator like Youngberg will make it into bread. You know? Didn't he made someone's flower baby into bread for the science faculty, I think. They left it alone, so he did a little slit and just took a couple cups of flour out and taped it back up. And apparently they noticed, and he got talked to as well. We were brought into the office, and not simultaneously, but you know, there it is. I bit the insides of my cheeks as I imagined the administrator that was assigned to explain this. Am I still recording? Crap. All right.